So we finished up our last problem talking about what a contingency table was, some general probabilities, a conditional probability, and probabilities and or probabilities. So we're going to focus a little bit more on this multiplication rule. And so this is, if you have 2 or even 3 events, how can you determine if they're independent or dependent? So we have what we call the multiplication rule. So 2 more useful formulas. It says if 2 events are dependent, then the probability of A and B is the probability of A times the probability of B given A. So if they're dependent, this second probability here is dependent on what happens with the first probability, right? If they're dependent. If the 2 events are independent, then the probability of A and B is just equal to the probability of A times the probability of B. Different ways we could see this. The most common way is whether they say with or without replacement. So if it's dependent, usually we say without replacement is common if they're dependent events, because if you choose something and then you set it aside, then when you go in to select, the second item, it's going to change your probability because you've already taken something out. Now, if they're independent, a lot of times this says with replacement. So just some other common words associated with independent or dependent events that we can see. Again, just as a note, we can use contingency tables to help determine if 2 events are independent or not. So in our last example, we found, let me scroll back up to what our contingency table looked like, right? So we were looking at whether the person was injured or not injured last year and they stretched or didn't stretch. So our last question we looked at, right, it was E, the probability that athletes stretched before exercising or injury in the last year, right? So we looked at this piece here. If we wanted to look a little bit more, if we look at letter D with A, so if we go back up to our last example, we'll see this contingency table, right? So this contingency table we looked at was the person injured in the last year, not injured, did they stretch, did they not stretch? And so this idea of the and probability is letter D, right? Athletes stretching before exercising and no injury in the last year. Now we could find this pretty easily from a contingency table, but sometimes we don't always have the contingency table. And how can you determine if something is independent, right, or dependent? So let's take a look here. So we know, right, the probability of A and B, right, this stretching before exercising and no injury, right, was 295 out of the 800. So we know if this is A, stretches, and B, no injury was B, then the probability of A and B, right, that was what we found with letter D, was 295 out of 800. So now it says, right, are they independent? So what we want to do is we want to find, does probability of A and B equal the probability of A times the probability of B? So if this is equivalent, then if we take the probability of A, so the probability of the athlete stretching, which if I scroll up a little bit, we actually found this. The probability of them stretching was part A, right? 350 over 800. So 350 over 800 times, right, the probability of B, they received no injury, which again, this was part B, so 514 over 800. If these are the same, then they are independent. So if you take, right, 350 times 800, right, and then, oops, sorry, it should be division. Let me go back and change that. It's divide. And now we say times 514 divided by 800. Right, we get, and let's do this as a fraction, right? Math, enter, enter, right? We get something that's way crazy. So what we'd say is these are not, right? They are not equal. So this means that the events are dependent. dependent. All right. So now that we know they're dependent, what does that really mean, right? So this means, right, that the no injury, right, was dependent on whether the person stretched. So that, no injury, depended on whether the person stretches. All right, so you can use this idea of, are they independent or dependent based on the different probabilities, looking at the intersection and then looking at the two probabilities separately to see if they're equal. So it says, while contingency tables are commonly used for conditional probability, it is not the only way we can be asked about conditional probability. So we have some multiple examples here that are other ways we can figure out conditional probabilities. So example 2 says, suppose you pick a card from a deck. What is the probability of getting a spade given that the card is a jack? So I always like to start out by writing what was given and what are we trying to find. So we're trying to find the probability of getting a spade, right? That's A. And given that the card is a jack, so that's B. So the card is a spade, given that the card is a jack. So my denominator corresponds to sort of what's been given. So if I'm told that the card is a jack, well, I only have 4 jacks in my deck. So I only have 4, right? 4 jacks in my deck. And of those jacks, how many of them are a spade, right? And we know that there's only 1 jack of spades. So my probability of a spade given that the card is a jack would be 1/4, or, right, 0.25. So for example 3, it says, suppose you pick a card from a deck. Again, this idea, right, just 1 card. What is the probability of getting an ace given the card is a queen? So I want the probability, right, that it's an ace given the card is a queen. All right, so if we know that the card is a queen, again, I have 4 queens in my deck, right? So 4 queens in my deck. Now, of those queens, how many of them are aces? And you might be looking and thinking, like, I'm not sure what you mean. Well, right, there can't be a queen of ace or an ace of queens, right? Those types of cards don't exist. So there'd be, right, there's 0 aces you can choose if we know the card is a queen. So this probability would be 0, or it would be impossible to occur, right? If you know that the card is a queen, it can then never be an ace. So, right, both of those, we're just picking 1 card. So now, with something like example 4, it says, well, what if you choose 2 cards from a standard deck of cards? What is the probability of picking a queen given the first card was a king? And usually if it doesn't say with or without replacement, a lot of times we just assume without replacement. So we're going to do this idea of without replacement for this one. So what is the probability of, right, picking a queen given the first card was a king? And this idea, right, so we're focusing on like the second card. So the probability of picking a queen given the first card was a king. So the idea is we're just focusing on the second card. So we're choosing 2 cards. We just want to find the probability of the second card. So I think of my deck. I have 52 cards in my deck, right? I choose, and I know I picked out a king, and we set it aside. So when I'm ready to go pick my second card, I have 51 cards to choose from. And how many of those are queens, right? And if I think I still have all queens in my deck, because I only chose a king for my first card. So I'd have 4 out of 51. And again, whether you need to simplify this or just reduce it and get a decimal, let's do maybe 3 decimal places. So 0.78 would be my probability for this one. So that's a probability of the second card being a queen given the first card was a king. So let's take a look at example 5. So it says, suppose you choose 2 cards from a standard deck of cards. What is the probability of picking a queen given the first card was a queen? So again, 2 cards, we're focusing on the probability of the second card. So the probability of the second card is a queen given the first card was a queen. So I think about what my denominator would be, right? We start with my 52 cards. I choose a queen. I set it aside because I get, again, sort of defaulting to without replacement. So I have 51 cards to choose from. And now if I think, right, when I go back in to choose a second queen, I had 4 queens to start with, but now I only have 3 to choose from since the first card that I took out was already a queen. So for this one, it would be 3 out of 51. And so my probability would actually be lower, right? Because we have less queens to choose from. So 5, 9 would be my probability. So we do have to be careful with, without replacement, we'll see my denominator decrease. But will my numerator decrease based off of sort of what happened with the first card?